All right, guys, last section of the year that we need to cover here is section 9.3, and the title of this is vague. The book itself just calls this graphical and numerical methods, but doesn't actually explain what these are graphical and numerical methods for. So what I've added here is a little bit of an addendum right there. These are methods for approximating solutions to differential equations. At this point, we have covered 9.1, where we learned what a differential equation was and how to come up with its solution, whether it's a general solution or a specific solution if an initial value was given to you. But unfortunately, there are some differential equations that are going to be so complicated for us that we're not going to be able to solve them through normal methods with separation of variables and the other things that we've talked about before. So two of the methods that we talk about here are how to graphically approximate a solution and then numerically approximate a solution. I'm going to cut this video up into two sections, and the first thing we're going to do is talk just about the graphical methods, and in the second video I will come back and talk about the numerical methods, although this one right here for the numerical methods, that is a topic that is only going to get covered on the BC exam, so most of you guys watching this who are going to take the AB exam probably don't need that second video. So we're going to focus, number one here, on what are called slope fields. And slope fields are the graphical approximation that I talked about here just a second ago to solving a differential equation. And then what I did right here, guys, is I went online and I found a wind map. And this was the first one that popped up, so I grabbed with this. And so we're looking at the Middle East right here, and usually if I just put this up on the board and say, okay, guys, what's happening here? People can generally follow it pretty well. All those arrows are pointing in a particular direction, and they represent the direction that the wind is blowing at that particular time. This is a pretty old map, everybody. October 25th of 2006 at 3 o'clock p.m. local time in Baghdad. So the arrows tell you what direction the wind is going, and one thing that a wind map has too, the color scheme right here that you can read on this line tells you the strength of the wind. So that purple actually means there's very little wind going on. But when you get to the spots where it's blue, oh, this right here and this right here, that's a little bit higher up. Now your wind might be blowing close to 10 miles, I guess that's meters per second, or about 15 miles per hour right there. So, the thought going on right here is that a wind map kind of tells you where, if you were to release something into the atmosphere, where it might go. Now, on something this size and something this scale with thousands of square miles, the analogy doesn't really hold, but in a smaller scale, if you were to drop something light, like, a plastic grocery bag, somewhere, like right around here in Saudi Arabia somewhere. Let's see, trying to think of the best color here to make that easier to see for you guys. Actually, I wonder if white would work well. If I dropped something right about here in Saudi Arabia and I asked you guys where this thing would go, you could kind of approximate the path that this object might take by kind of following, here's a little swirl here, by kind of following the direction, that's a little bit weird, that this thing might end up taking. Or if I were to drop something over here on this northern end of Iran, that might swirl here and come down a little bit. And I'm basically just following the arrows here. And I can get a sense, not perfect anyway, but I can get a sense for where this object might end up going then, kind of following those wind currents there. Well, a slope field works in a similar way, everybody. I should get rid of my white pen because that's not going to help me much when I go to write on a white page. Anyway, a slope field is kind of like a directional map that shows you where something might go. So, I'm not going to spend a whole lot of time trying to define it. I think it's one of these things we will better be able to understand just by doing. I got 4 examples for you here. And I'm going to start off with one that is so ridiculously easy to get the hang of, you're not really going to feel like you understand anything at the end of this one. But I promise you, once we get to a more complicated one like B, or then C and D, where things really get interesting, I think you're going to start to get the sense for what's happening. So the first thing I want to point out is that if we're going to draw a slope field, that is a graphical approximation method for solving a differential equation. And sure enough, what were we given right here? That is a differential equation. Ooh, nope, 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 nope. All right. That is a differential equation. We've been given the derivative of y with respect to x is equal to 1/2. Now, all we do with a slope field is we are going to draw a tiny little line segment at every point where they tell us to draw one that has a slope equal to this derivative right here. Because after all, what does dy dx tell us? The derivative is the slope of our tangent line. So this is a very unusual example because your derivative is a constant. Now that means it doesn't matter what the values of x and y are. The derivative of this function is always going to equal 1/2. So no matter where we are on this graph, the slope of our tangent, or the derivative of the function itself, will always have a slope of 1/2 or 1/2. So on this graph, and I took this off of the worksheet that I think you guys are going to be doing for me here for 9.3 homework, we have got, I don't know, let's see, it is a 5x7 array here. So we've got 35 different dots on this graph. And normally I won't ask you to do this many, but you'll see the pattern here, and this goes quicker than it sounds. But at each of those 35 points, we're going to draw a tiny little segment that shows, how do I translate this? A slope of 1/2. So what does a slope of 1/2 look like? Up 1 and right 2. So from the origin, right over here, I would think about drawing a slope of 1 up and 2 to the right, which would be a segment that looks something like that. Now, if I was drawing the whole tangent line, I would go ahead and draw this whole thing looking like that. But we're not doing that. With a slope field, we're just drawing one tiny little segment here that passes through the point 0, 0 with a slope of 1/2. Now we would repeat that process for all other 34 points in this graph, or however many you have. And I know that sounds crazy, but in this one, well, it's going to go pretty quick and easy. Every one of them is exactly the same. It doesn't matter where you are, but the slope of every one of these little tangent segments is going to be positive 1/2. So every one of them is rising as we read it from left to right, and it's rising at a slope of 1/2. So, okay, I don't know that I'm going to do all 35, but I think you guys get the point here. So, because this derivative is constant, the value of the derivative, or the slope of the tangent, does not depend on the x or the y coordinates. So that's your slope field there, guys. I certainly didn't draw it perfectly, but that means that every single point on that graph, everybody, would have a slope to it equal to 1/2. So let me be clear, we're done with that example. Now, what I want to try to illustrate is not what you are going to be asked to do with any of these problems. But in this particular case, this is a differential equation that could actually be solved. The first thing I would do is bring the dx over to the other side and get dy is equal to a 1/2 dx. And then I would integrate the left and integrate the right. Integral of dy is just going to be y, and the integral of 1/2 with respect to x is a 1/2 x plus c. So that, everybody, is the general solution to this differential equation. So what the slope field actually does, kind of like I was drawing those little arcs there in white, kind of following the direction and the pattern of the arrows, slope field does the same thing. If I were to think about a couple of different values of c, like, oh, I don't know, y equals a 1/2 c plus, I'm sorry, that should be a 1/2 x. That didn't work. And then how about a plus 1 right there? If we were to try to graph this solution, it would start right here with a y-intercept of 1 and have a slope of 1/2. So up 1 and 2 to the right. So this line would look something like this. And the point that I'm hoping you guys see here is that that line fits very, very neatly within the direction of the slope field. Okay, it wouldn't be a line like y equals, negative 3x plus 2 that would look something like this, because that one completely contradicts what's happening in the slope field. It's going completely the wrong way. But y equals 1/2 x plus 1 fits in there really nicely. What if c was something different? What if c was negative 2? Y equals 1/2 x minus 2. Now we'd be starting right here. And with a slope of 1/2, up 1 and 2 to the right, this solution curve would look something like that. And guess what? That one also fits very, very nicely within the slope field. So the slope field is just kind of showing you what direction the solution curve would need to go in, and it gives you a sense then, everybody, for what the solution would look like, even if the solution were too complicated and you weren't able to come up with it by simply solving the differential equation. So to be clear, everything I did in green and red at the bottom of this page is not what you're going to be doing on your homework. So in fact, I should get rid of all of this now. You can rewind the video if you want to see it again. This is where we would have stopped. That's the slope field for this differential equation. Now, as I said a few moments ago, that example is so simple, you're not really going to feel like you understand it at the end. And I don't think it'll be until we get into more complicated examples like B and especially C and D with two variables in there that you're going to be able to really understand what's going on. So this one, let's take a look at, and I think you can see this one's a little bit more complicated because it contains a variable. But it's the same basic concept. Our derivative now, the slope of our tangent, is 1/4 times x. So what you're going to do is think about any of the 35 points here, and you got to start somewhere. I always like to start at the origin. So at the origin, which last I checked is right there, the coordinates obviously are 0, 0. And if I were to evaluate, you're not really going to write this down, guys, but if I were going to evaluate the expression 1/4 x at the origin, 0, 0, well, what's that going to get us? That's going to be 1/4 times an x coordinate of 0, 0. So I've got a horizontal tangent segment right there at the origin because the value of 1/4 x, where x is 0, is going to be 0. And of course, a segment or a line with a slope of 0 would be horizontal. Now, one of the nice things about certain slope field problems is 35 points sounds like a lot. I get that. However, there are patterns that emerge here, and I kind of said one a second ago, and I don't know if you noticed. See if you can answer this question for me. This derivative here, 1/4 x, will equal 0 anywhere what happens? 1/4 x will equal 0 anywhere that x is 0. That happens at the origin, but it also happens at the point 0, 1. So that's going to be horizontal as well, and 0, 2, and 0, -1, and really anywhere on the y-axis. So at all 5 of these points, they all have the same x coordinate. So since this derivative is expressed solely in terms of x, all 5 of those derivatives are going to be the same, and the slope fields are going to look the same. How about right here at the point 1, 0? Now, if we plug a 1 in here for x, 1/4 times 1 is 1/4. So I'm going to draw a little segment here with a slope of 1/4. And guys, I'm not going to pull out my protractor here and measure to make sure that you've got this right. All that's important is that 1/4 is a positive slope, but one that's barely positive, and it's rising very slowly, so it might look something like that. The y-coordinate here is irrelevant because there is no y in this derivative. And the same thing happens at the point 1, 1. 1/4 times 1 is 1/4. And the same thing at 1, 2, and 1, -1, and 1, -2. Let's keep going now. Over to the right here now, where x is 2. 1/4 times 2 is 1/2, which is still increasing at a pretty slow rate. This just needs to be a little bit steeper than the little segments that I drew a moment ago. And now if I push to the right even further, now when x is 3, now my slope becomes 3/4. So still positive, but steeper than the one that I had before. And I feel like I'm drawing all of these maybe a little bit too steep. Honestly, that looks steeper than 45 degrees to me. That looks more like a slope of 4/3 rather than 3/4. But I don't care, and you guys don't need to care. It doesn't have to be super exact. How about over to the left? Okay, anywhere to the left here, like for example this point right here, our x coordinates are all going to be negative now, so our slopes are going to be negative. 1/4 times -1 is -1/4. And I'll just do that same thing here, and here, and here, and here. Pushing to the left further, when x is -2, now will be -1/2. Just a little steeper than what I drew before. And now over to the left again now, where x is -3, our slopes will be -3/4. So a little bit steeper there as well. And I'm hoping you guys are starting to see my point here. 35 points sounded like a lot to have to think about slope fields at, but in certain cases, when you start to recognize some patterns, you can take some shortcuts and get done a little bit quicker. Now again, we are done with example B, but if you cared, this is another Diffie-Q that we could solve. Again, I'd separate my variables here and get dy is equal to a 1/4 x with a dx at the end of that. We would anti-differentiate both sides, and we would get y equals, oh boy, we have to increase the exponent by 1, that's an x squared, and then divide by that new exponent. 1/4 divided by 2 is going to be a 1/8 x squared, and a plus c at the end. So pick a c value. I'm going to pick -1 right over here. So the one possible solution curve here would be y equals 1/8 x squared minus 1. Well, that would be an upwards opening parabola that would pass through the point 0, 1 and look something like that and fit that solution curve very, very well. Okay, so that's just kind of what I'm doing in green and red at the end is just a way of trying to tie all this together for you guys, for helping you to figure out what exactly it is that we're accomplishing with this slope field. And just a reminder that in a lot of cases, this work right here will not be possible. The Diffie-Q itself is going to be too complicated for us to solve, and the slope field just kind of tells us where the solution curve might fall and what the solution curve might look like. So, A was a constant derivative, so everywhere it was drawn exactly the same. B, this derivative had an x in there. The y value was irrelevant, but the x value mattered, so this slope field was consistent in columns. Okay, what do I mean by that? All 5 of these points right here had the exact same value for the derivative because they had the same x-coordinate, and their y-coordinates did not matter. However, both of these two examples we've done so far, A and B, are kind of the exceptions. And the norm is what you're going to start to see right here in C, where your differential equation is going to be expressed both in terms of x and in terms of y. So now we got to start thinking a little bit harder about what this is going to look like at our 35 points here. Now, by the way, this will show up on the AP test, everybody, but most of their slope fields that they ask you to evaluate, they usually have you draw it at like 8 or 12 spots, not 35, so relax. It's not that bad. Okay. Now, y over x. I now have to pay attention to both my x and my y coordinate, and that can be a little bit tougher. But again, I want you guys to look for shortcuts. This derivative is a quotient, y divided by x. And if I were to ask you guys, what's the number one thing you need to watch out for when you're dividing? What I'm hoping you guys would tell me is that you cannot divide by 0. The denominator of this fraction is x. And anywhere that x is equal to 0, this derivative is undefined. So, where is x equal to 0? Well, we had that conversation back over here in B. It's on the y-axis. Anywhere here on the y-axis, your x-coordinate is equal to 0. And in example B, 1/4 times 0 got you a slope of 0, which translated then to a horizontal line segment here for your slope. Now, on this example, things are a little bit different. It's still true that x is always equal to 0 on the y-axis here itself. But I want you guys to think about what happens if we were to put a 0 in for x. You would get some number divided by 0, and it's fair and accurate to say, therefore, that the slope of that line is undefined. And that is correct. So a lot of people, though, think they're done and they don't have to draw anything when x is 0. That's not true. The slope here is undefined. But if you ask yourself what kind of line has an undefined slope, there's an answer to that, and it's vertical. So now we're going to draw a very small vertical tangent segment at each one of these 5 points where our x-coordinate is 0. And what you notice right there, guys, that almost looks like a dashed line. There's a reason for that. We'll get to that in a little bit. All right, so the first thing you should look for in a case like this is where is the denominator equal to 0, and you draw vertical line segments there. Follow-up question. The second thing you should look for with division, other than dividing by 0, is if your numerator is equal to 0. And if the numerator is equal to 0, 0 divided by any number other than 0 is equal to 0. So you want to be careful here. We're now going to draw our horizontal tangent segments. That will occur not just anywhere that y is 0, anywhere y is 0, but x is not. So I think we're going to have 6 of those points here, here, and here. But guys, this is really important, not at the origin. At the origin, you end up with 0 over 0. And I know this sounds silly, but the 0 on the bottom trumps the 0 on the top. It's more important. And 0 divided by 0 isn't 0, it's undefined. So we would not have a 0 slope field there, but we'd have one here, and one here, and one here. So what it kind of looks like we've drawn here, guys, is a vertical asymptote at the y-axis and a horizontal asymptote at the x-axis. That's exactly what we've drawn. Okay, now from here, what are we down to, guys? 6 points in each quadrant, 24 more to go. Let's do it. Next thing I would look for, this is just me, where would this thing equal, where would this derivative equal 1? It would equal 1 anywhere that x and y were the same value. Like, for example, at the point 1, 1. Our derivative would equal 1. And the same thing would happen at 2, 2. The same thing would happen at -1, -1, and -2, -2. Cool. That's it. All right, next question. Where would this thing equal -1? That would happen anywhere that x and y were opposite values, like 1, -1, 2, -2, -1, 1, and -2, 2. Boy, those almost look like asymptotes as well. And now from here, guys, I don't know that there's a whole lot of shortcutting to be done. Now, with the remaining 16 points, you might just want to think about things. For example, at this point right here, that is the ordered pair 2, 1. So if we put a 2 in for x and a 1 in for y, we get a slope of 1/2, pointing right back towards the origin. Interesting. Next to it, right here, at the point 3, 1, we would get 1/3, which would also be pointing back towards the origin. I think I see a pattern. Up here, at the ordered pair 3, 2, we would put a 3 in for x and a 2 in for y. We get a slope of 2/3. Down 2, left 3, also pointing back towards the origin. And this point right here, at 1, 3, a 3 on top, at 1, 2, my mistake there. We'd have a slope then of 2 over 1, also pointing back towards the origin. And guys, that concept of pointing towards the origin is something we definitely should be noticing, because that's going to end up carrying you through the remaining 15 or whatever we had left at this point. But it looks like every single time we do this, our slope field is pointing right back towards the origin, which we had before. So kind of this cool like starburst explosion pattern that we had going on right here. Yeah, just for fun. Again, this is not something you would be doing, but if we were to try to solve this differential equation, that would be a 1 over y times dy equals a 1 over x times dx. And then we could anti-differentiate both sides. This is going to be interesting. Natural log of the absolute value of y would equal natural log of the absolute value of x plus c. We'd get rid of the natural log by exponentiating both sides. We'd get rid, let me slow down right there, cowboy. So the absolute value of y would equal, it would be e to this whole power, e to the natural log of the absolute value of x plus c, which equals, to put it another way, e to the natural log of the absolute value of x multiplied by e to the c. And this hasn't come up yet in anything that I've done with you, but a lot of times in the solution, they look at e to a constant power and realize that since e is a constant, e to a constant power is just another constant. They're just going to make this a c, but most of the work that I've seen generally makes that a capital C. Then they bring it out in front. c times e to the natural log of the absolute value of x. And then to get rid of the absolute value on the y, we end up with just a plus or minus in front of that. Although plus or minus a constant is just a constant. So I'm going to leave that as c times e to the natural log of x power. All right, that's kind of how this one ends up right here, and it doesn't really show us a whole lot, but basically then we end up with, if you think about a value for x right here and what c might be, the e and the natural log are really just going to drop each other out. So this really, I guess I should have realized this, becomes c just multiplied by the absolute value of x. Guys, that's a linear function with no y-intercept, so it's passing through the origin. So I don't know, if c were 2, it might be the line y equals 2x, which would kind of look something like that. If c was 1/3, it might look something like that. Okay, so again, just kind of trying to illustrate what it is that we have accomplished here, but the slope field was really the important point. All right, and the last example I wanted to do with you, this is one that, if I'm not mistaken, came off of an AP test. We might see this in some of our work a little bit later on, but let's see what's going on here. Our derivative now is equal to the quotient y minus 1 divided by x squared. Okay, so let's look for shortcuts. First of all, where is this thing undefined? It's undefined anywhere your denominator is 0, and x squared is going to be 0 anywhere x is 0. And once again, that happens on the y-axis. So at all 5 of these points, because x is 0, our derivative would be undefined. What's next? Where is this thing going to be horizontal? It's going to be horizontal anywhere that its numerator is equal to 0, but its denominator is not. And the numerator, y minus 1, will equal 0 anywhere that y is 1. So that'll happen here, 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 not at the point 0, 1, because at 0, 1 we end up with 0 over 0, which is undefined. But here, and here, and here. Now, that leaves us with, I think, 24 more points to do. There's a little bit to be gleaned out of this and gained here, and I want to kind of illustrate the point here real quick. What I'm going to do, guys, is move just right of the y-axis, and I want to talk about the 4 points in this column right here. Now, because this diffie-q contains both x's and y's, we've got to sit here and do the grunt work on this, everybody. So let's focus on this one right here. At the ordered pair 1, 2. 2 minus 1 is a 1 on top. 1 on bottom squared is a 1 as well. So at the point 1, 2, we get a slope of 1. It's going to look something like that. I think as I move down from here, this is probably all now going to change. For example, at this point right here, I'm dealing with the point 1, 0. A 0 in for y gives me a negative 1 on top, and a 1 in for x gives me a 1 on bottom. So this is now negative 1 over 1, which is negative 1. Let's keep going down from there. At the point 1, negative 1, I'm going to get a negative 2 over 1. That slope is going to be negative 2. And then right below that, at the point 1, negative 2, I'm going to get a negative 3 over 1. Okay, and that's going to look something like that. So all 5 of the points in that column there on the line x equals 1, they're all different. But I now want to point something out here, guys. Let's take a look at what happens in this column right here when x is negative 1. So I'll start right over here, guys. And at the point negative 1, positive 2. When I put a positive 2 in for y, my numerator is 1. The negative 1 on the bottom gets squared and becomes 1 again. So I'm going to get 1 over 1. Once again, I'm going to have a slope of 1, which you'll notice is exactly the same as this slope that I got right here. Wonder why that is. Let's talk about this point right here, negative 1, 0. Negative 1, 0, I've got 0 minus 1, which is negative 1 on top. Negative 1 squared on bottom is positive 1. So negative 1 over positive 1, this slope is negative 1 also, the same as this one right here. Okay, when I put in negative 1, I'm going to end up with a negative 2. When I put in negative 1, negative 2, I'm going to get negative 3. So what have we learned here, guys? These two columns have the exact same slope at every one of their points. And the very good reason for that, everybody, is that this function's only x is being squared. And it doesn't matter whether x is equal to positive 1 or x is equal to negative 1, because if the one and only thing you're going to do with that x value is square it, this is an even function, at least in terms of how it behaves in terms of its x-coordinate. So that's going to save me a little bit of time here as well, although frankly, this one's still a little bit tedious. Let's focus right here on the point 2,2. That is a 1/4, and I think I've learned my lesson. That's going to be a 1/4 there as well. How about right here at the point 2, 0, -1/4. So a -1/4 here, and the same thing right here. Below that, at 2, -1, that is a -2/4, so that's a -1/2. Same thing right there. And below that, at 2, -2, that's going to be a -3/4, which is going to be a little bit steeper than what we had drawn just a second ago. And the last column, let's go right here, guys, to the point 3, 2. A 2 on top minus 1 gives me 1. 3 squared on the bottom is 9. So while that's 1/9, that is barely positive. Same thing is going to happen right here. Okay? Down below that, at the point 3, 0, that's a -1/9. Okay, same thing right over here. And I think I get what's going on. I think this one's going to be a little bit steeper, but let's find out. At 3, -1, that's a -2/9. A little bit steeper, but not much. And then over here at 3, -2, that is a -3 and 9. That's a -1/3 on the bottom. Going to look something like that. Okay, so that's our rather interesting looking slope field for that one. And I don't know that trying to solve that one is really going to teach us a whole lot. So, all right, guys, that's going to be a wrap here on the first video from section 9.3. When I come back and record the second one, we're going to talk about Euler's method, which is a way of coming up with a numerical approximation to all the solutions within a differential equation. But for now, hopefully that gives you a pretty good sense for what's going on with slope fields. This, coupled with that worksheet packet that I stole from a conference I was at one time, I think is going to get you a pretty good start on that. So give that homework on 9.3 a try, and let me know when you guys have some questions. Good luck.